Hey guys, Jake here coming at you with another math lesson today. Doing something a little bit different today. Unfortunately, I wasn't going to be available on my normal Monday at 5 o'clock Pacific time to live stream, so I figured I would just do the same kind of video ahead of time and upload it at 5 Pacific for you. So hopefully you like this style. Be sure to drop a comment below if you prefer a live stream versus doing it this way. As always with my live streams, if you have any questions along the way, go ahead and drop them in the comments. I know it's not live. I won't be able to answer them live, but I'll definitely be coming back and looking through the comments and try to answer any questions I see there. So feel free to drop any questions you have along the way. We're going to be going through some critical numbers examples today. So critical numbers is one of the topics covered on my Calculus 1 study guide. It is available for free. If you want to go check that out, I'll put a link down in the description below. It is also covered in my complete Calculus 1 package. There's a link to that down in the description below as well. So be sure to check those two things out if you are interested in those. They should be very helpful to you, I think. But let's go ahead and jump into the examples here. So this first one, we're just going to be finding the critical numbers of this function here. F of x equals x cubed plus x squared plus x. So in general, when you're trying to find the critical numbers of a function, there's going to be two things that can cause a critical number to exist, or basically two kind of conditions you want to look for of which x values would be considered critical numbers of a function. The first is going to be wherever f prime of x equals 0. So basically you need to find the derivative of the function and set it equal to 0 and solve for x. The other one, which is equally as important, although I will admit it comes up less often, but you do still always need to check it, because if you don't check it, you might miss some critical numbers, is going to be wherever f prime of x does not exist. So you always want to be thinking whenever you're doing these critical number examples, which in either case, what you need to look at is the derivative of your function. So in general, you're always going to start these critical number problems, or any sort of a problem where you have to find critical numbers of a function. The first step is always going to be to find the derivative of your function. That's basically where you're always going to want to start. Then from there, we'll think about how to actually use that to find the critical numbers. So first of all, to take the derivative of this function, in this example, we can just use the power rule. So we can bring the 3 down in front, leave our x as x, subtract 1 from the power, leaving us with 3x squared for this first term. Then the derivative of x squared, again, can be power rule. We bring the 2 down in front, leave the x as x, and then minus 1 from the power. 2 minus 1 is just 1. X to the first power is just x. So I'm just going to leave that as 2x. And then the derivative of x is always just going to be 1. So here's our derivative. So now there's two things we need to think about. Where does our derivative equal 0? So the first thing we want to do is set this equal to 0. Okay. And the other thing we want to think about is, where does our derivative not exist? Where does this function right here not exist? Well, let's think about what this function is. This is a polynomial, right? 3x squared plus 2x plus 1 is an example of a polynomial function. Polynomials exist for all x values. They exist for all x values. They're continuous for all x values. Their derivative exists for all x values. This right here was a polynomial. The derivative of a polynomial is just going to be another polynomial. So this derivative here, this f prime of x, there's not going to be any x values where it does not exist. So in this case, we don't need to worry about this condition because it exists everywhere. As a result, we really just need to worry about this one. But like I said, you always want to think about this condition here. You always want to think about where your function's derivative does not exist. In this case, we're just going to have the solution to this equation, though, giving us our answer. So we need to figure out if there are any x values where 3x squared plus 2x plus 1 equals 0. So how could we try and figure that out? Well, typically the best place to start with a polynomial like this, setting it equal to 0, is to factor it out. How can we factor this out, though? Because we have a bit of an issue here where if you kind of think about the ways that this could factor out, basically we need two numbers that multiply to give us 3, which is going to be 3 and 1. There's not any other ways to factor that out. And then we need two numbers that multiply to positive 1. So that would just be 1, positive 1, and positive 1, or negative 1 and negative 1. So really we only have two choices here. We could either say plus 1, or we could say minus 1 and minus 1. Let's think about how those would end up factoring out, though. If we were to kind of reverse engineer this, we would get 3x squared, so that's good, and then negative 3x minus x would be a negative 4x, not a plus 2, right? So that's not going to work. And then similarly, if we were to put plus 1s here, we would get plus 3x plus x, so that would be a plus 4x. So there's not going to be a way to factor this out like this, which is kind of a bummer. That's generally going to be a lot easier if you can do it. But it's not the end of the world if you can't do it. The other option is to use the quadratic equation. So let's go ahead and do that. The quadratic equation just tells us that we're going to have x equals so negative b. So there's a little song that kind of goes along with this. I always have to kind of sing the song in my head. The opposite of lowercase b plus or minus the square root of b squared minus 4ac all over 2a. So the opposite of lowercase b, where this coefficient is a, this coefficient is b, and then this constant is c. The opposite of lowercase b plus or minus the square root of b squared minus 4ac all over 2a. So let's think about how this will simplify here. We're going to get negative 2 plus or minus the square root of 4 minus 4 times 3 times 1 is 12. So without even going further, you can see right here, we're going to have 4 minus 12 within the square root here, which is negative 8. So we're going to have the square root of negative 8. Well, that's a big problem because you can't take the square root of a negative number. So whenever you have a negative in here, that right there tells you there are no roots here. There are no real roots. There's only imaginary roots. So basically, there's no x values that make our derivative equal 0. So in this case, we're kind of running into some issues with solving this this condition of taking the derivative and setting it equal to 0. We're not going to get any like real x values that cause that. So let me actually check something real quick here. Probably should have looked this up beforehand. Okay, perfect. So basically what this tells us is that this function here does not have any critical numbers. There's no places where the derivative equals 0. There's no places where the derivative does not exist. So this function actually does not have any critical numbers. And that's really it with this problem. There's really nothing else we can do there. So that's going to be the final answer for that one. All right, so let's go ahead and go on to this next example here. We're going to find the critical numbers of this function now, where g of t equals the absolute value of 3t minus 4. So in this case, we have an absolute value. Finding critical numbers with absolute values is a little bit weird. And the reason I say that is, again, kind of going back to our main conditions, we need to look at where the derivative of this function equals 0. And we need to look at the places where the derivative of this function does not exist. Okay, so let's think about what this function would look like here. Basically, whenever you have an absolute value like this, what that is going to generally create in a graph is you're going to have your graph of your function, and basically whatever, in this case, we're taking the absolute value of everything. There's no other like pieces of our function. Like, for example, if we had a +1 out here, there's no pieces of our function outside of the absolute value. So what that essentially means is if you were to think about graphing this function, what you could do is graph the function itself without the absolute values, and then just flip anything below the x-axis to being above the x-axis. So we could basically just graph the line 3t minus 4, which would be something like this, a linear function with a slope of 3 intersecting with the y-axis at -4. That was just a really quick sketch to kind of demonstrate my point here. To then take this graph and turn it into the absolute value of 3t minus 4, we just have to take this portion that's below the x-axis here and mirror image it to be above the x-axis. So basically create a mirror image of that line down there, but putting it above the x-axis. So essentially we just have this like v function here, and now this would be gone. So this positive reflection, anything that's above the x-axis before is going to remain unchanged, but anything that was negative, anything that had a negative y value, then just becomes positive. So that's what this function is going to look like. When you're taking the derivative of this function, something weird happens basically just right here at the kind of sharp corner edge where you kind of flip from the original linear function to the mirror imaged side of it. And the reason for that is basically there are infinitely many tangent lines that could intersect with that point of our function that have different slopes. So whenever you have a sharp corner like this in a function, that's generally going to be a place where the derivative of the function does not exist. So essentially this kind of sharp corner is a place that we want to consider a critical number. Now, how do we actually figure that out? There's kind of two approaches we could take here. The first one would be to graph it and look at where this corner is, and then we could kind of think about how we might figure out what x value makes that situation happen. The other one is to think of this absolute value function as a piecewise function, right? Because basically we know that this linear, or this function here, g of t, is going to be exactly the same, like I just said a moment ago. It's going to be exactly the same as whatever this linear function is for all x values that are, or for all y values that are positive, which we just figured out is basically from here to the right. It's just going to be 3t minus 4, right? That function is just going to be 3t minus 4 whenever we have x values that are greater than or equal to this point right here where it intersects with x equals 0. So basically, we would want to figure out where 3t minus 4 equals 0, and everything to the right of that is going to just be 3t minus 4. Okay, and then everything to the left of it is just going to be the flipped version of 3t minus 4. Well, to figure out the kind of flipped over version, all you have to do is make your negative y coordinate into a positive y coordinate, which means you're essentially just multiplying it by -1. So for all of our x values that are less than this corner point right here, all we have to do is multiply all of our output values of 3t minus 4 by a negative. So we're essentially just kind of splitting it into our positive half and our negative half, where we have to actually do something with the absolute value by multiplying it by -1, and the part where we don't have to do something to it. So essentially, we kind of split it based on wherever this equation equals 0, wherever our original equation equals 0. Okay, we haven't really gotten to the critical number part here. What we're trying to do first is think of this absolute value function as a piecewise function. So we just need to solve this to get, and actually I should not have said x here, I should have said t. Okay, so we're going to get basically whatever the solution to this equation is tells us where this corner of our absolute value function is and where we would split our piecewise function. So doing that, we just add 4 to both sides, giving us 3t equals 4. Divide by 3 gives us t equals 4/3. So basically for t greater than or equal to 4/3, we're not going to do anything to our function because 3t minus 4 is a positive number, or 0. And for any t values less than 4/3, we need to plug it into our 3t minus 4 and then multiply it by -1, because it's going to be 3t minus 4 is going to be negative for t values less than 4/3. So if we multiply them by a negative, then that makes them positive, which is exactly what the absolute value would do. So this piecewise function is equivalent to this absolute value function. So now what we need to consider is finding the derivative, right? We need to find g prime of t and see where that equals 0 and where that does not exist. So to find the derivative of a piecewise function, you pretty much can just find the derivative of each of its pieces and keep the domains the same. There is one kind of little thing we're going to have to do that to kind of account for that. So let's think about the derivative of this piece here, 3t minus 4. Well, the derivative of 3t is just going to be 3, and then the derivative of a constant is 0. So that derivative is just 3. Then let's think about this piece here, negative, and then parentheses, 3t minus 4. Well, first let's think about simplifying this function. We have this negative sign here that needs to distribute to the 3t and to the -4, which basically, if we distribute that into the parentheses there, we're just going to get -3t plus 4. So the derivative of this function is just going to be -3 plus 0, so -3. Okay, so really the only thing that's going to be weird here is our bounds. And the only place that it's actually going to be weird is right at this spot, this t value where we switch from one function to the other. And the reason for that is, if you think about the definition of a derivative, the limit definition of a derivative, it takes into account a two-sided limit. It takes into account essentially what it's getting at is what slope is your function approaching at any given point from both sides. Well, when you have a piecewise function like this, and it's kind of split into two different sides like this, we can't include all t's greater than or equal to 4/3 in this domain here of this function, because this really is only going to tell us about the slope of this portion of our piecewise function to the right side. It's not going to account for the left-sided limit. And I don't really want to get into the nitty-gritty of what I mean here. Really, my point here is that when you're taking the derivative of a piecewise function like this kind of method of just taking the derivative of each piece is okay, but you do want to be careful that we can't really include the endpoints of these domains into that. There's kind of an additional step that we would need to go through to verify that that this function has the same slope at that point. Since to the left of t and to the right of t equals 4/3, we have two clearly different slopes, right? One of them is 3, one of them is -3. We're not going to be able to say that this derivative kind of continuously flows from -3 to 3 right at 4/3. So what I'm getting at here is that this method of splitting it into the piecewise function, it confirms what I was telling you before, that this harsh corner of our absolute value is going to be the place where we have an issue. And really what all this shows is that g prime of t, our derivative of our function, it's not going to exist at t equals 4/3, right? So t equals 4/3 is the place where g prime of t does not exist. So this is going to be a critical number based on this condition right here. Now, we also need to consider, where does this function equal 0? Well, we can see for all t values greater than 4/3, g prime of t equals 3. So 3 does not equal 0. 3 is never going to equal 0, no matter what t value you have. So similarly, we're also going to get the same thing here for all t values less than 4/3. G prime of t is -3. -3 never equals 0. So there are no places where g prime of t equals 0. It's not going to be, this doesn't equal 0 for t's greater than 4/3 or less than 4/3. And at t equals 4/3, it also doesn't equal 0 because it does not exist. So in this case, we only have one critical number, t equals 4/3, and it occurs where g prime does not exist. And there are no spots where g prime equals 0. So that's going to be our only critical number in this example. Okay, so let's go ahead and go into one other example here. We're going to find, again, same thing we've been doing. Find the critical numbers of the function. In this example, we have h of p, our function h of p equals p minus 1 all over p squared plus 4. Okay, so again, to find the critical numbers, we are always going to want to consider the same two things. Where does the derivative of your function equal 0? Where does the derivative of your function not exist? Those are always going to be the two conditions that create critical numbers. So you just need to figure out what p-values make that happen. Before we get into this example, I do want to just throw out one thing. If you are getting some value out of this video, please do me a favor and hit that like button down below. If you appreciate me coming on and doing this this version of this video, even though I wasn't available for a live stream this week, hit that like button. Huge help to my channel. So anyway, thank you for that. Let's go ahead and jump back into the scheduled programming. So first step is going to be to find h prime of t. We need to find the derivative. Finding the derivative of this function is just going to use the quotient rule. Quotient rule just says that we're going to call the numerator of our function f, the denominator g. We then need to find f prime and g prime. So the derivative of the top of our function, the derivative of p minus 1 is just 1. And then the derivative of p squared plus 4 is going to be 2p. And that's just based on the power rule. Okay. So then quotient rule says you're going to take, to find the derivative of your function, you're just going to take low d high. So low times the derivative of the high, the bottom of your fraction times the derivative of the top. So p squared plus 4 times 1, which is just p squared plus 4. Minus high d low, so minus f times g prime, minus high d low, p minus 1 times 2p. And make sure you do put these in parentheses because this minus sign is going to need to distribute to all this stuff. Okay, then that's all going to be over the bottom of your fraction squared. Okay, so let's think, before we go ahead and continue with simplifying this, let's think about these two conditions here and this derivative we found here. So this derivative is the derivative of our function. We could definitely simplify it, but before we do that, let's think about this. What would cause a fraction like this to equal 0, right? We want to figure out where h prime equals 0. Here's h prime, this fraction. Where does it equal 0? Well, it's going to equal 0 wherever the numerator of your fraction equals 0, right? 0 over anything is 0. So really, to satisfy this first condition, we just need to figure out where the numerator of our fraction equals 0. Okay. Where is a fraction not going to exist? A fraction does not exist when the denominator equals 0, right? So if the denominator equals 0, then you're getting some number divided by 0. Well, that basically breaks a rule of math. You can't divide by 0. That's not a thing you can do. So if you're ever dividing by 0, if your denominator ever equals 0, then your function does not exist there. So we need to figure out where our denominator equals 0. If either of these two things happen, then one of these two conditions will be met, and that tells us that that p-value is a critical number. So basically, these are the two equations we needed to solve to find the critical numbers of our original function h of p. Okay. If that's making sense so far, go ahead and drop a comment below. Just say, got it so far, so I know you're following along. If that's confusing you, let me know that in the comments as well, and I'll see if I can provide a little more clarification on that. So let's go ahead and think about how to solve these equations. Let's just go ahead and kind of distribute this out over here and simplify this. So we'll leave our p squared plus 4 alone for a minute. The 2p will multiply into both of these terms here. So we're going to get 2p times p is 2p squared, minus 1 times 2p is minus 2p. Then we need to distribute our negative sign in here. So that's going to be p squared plus 4 minus 2p squared plus 2p. Okay, then we can combine our negative 2p squared and our positive p squared, giving us negative p squared plus 2p plus 4 equals 0. And then we would want to see if we can factor this out, which I don't think we're going to be able to factor that out. It's not going to factor nicely in this case. No, it's not going to work out very nicely. So what we can do is use the quadratic equation. So p is going to equal the opposite of lowercase b plus or minus the square root of b squared minus 4ac all over 2a. Oops. In this case, a is -1. And then from there, we would want to basically solve that out. So -2 plus or minus the square root of 4. These negatives here are going to cancel. So we're going to get plus 4 times 1 times 4 is 16. So 4 plus 16 is 20. All over -2. So let's see here. We can kind of factor out a 4 out of this, giving us -2 plus or minus 2, because when you factor a 4 out of a square root, you have to square root it, leaving you with 2 times the square root of 5 all over -2. Which then is going to simplify down to basically this negative can kind of cancel with all these. So we get, and then the 2 is going to cancel with all these, turning all of them into a 1. So we get 1 plus or minus the square root of 5 all over 1. So 1 plus root 5 and 1 minus root 5 are 2 of our critical numbers. Then we just need to solve this equation. So if we square root both sides, we get p squared plus 4 equals the square root of 0, which is just 0. And then we minus 4 from both sides. P squared equals -4. Square root. Well, you can't square root a negative. So this equation, actually, there's not going to be any p-values that cause our denominator to equal 0. And so as a result, there's no p-values where h prime of p does not exist. So we're just going to have these 2 critical numbers from the p-values that make h prime of p equals 0. So this is going to be our final answer, just these 2 critical numbers here. All right. So that's it. If you did get some value out of this video, do me a favor and hit that like button down below. Huge help to me and my channel so we can spread these videos out to more people. And if you have any questions, throw them in the live chat down below, and we'll see you next time.